So in this first demonstration, I have these two blocks here. They look very similar, they're both black, they're both dark. And what we're going to do is we're going to see one of the differences between what we call conductors and insulators in transferring energy. So what I'm going to do is these are both sitting at room temperature. They are about 20 odd degrees. And I'm going to put an ice cube on both of them. This is made of a plastic, this is made of a metal. So when I put the ice cubes on them, we're going to see what happens. Before I do that, think to yourself, is there going to be a difference between the way the ice cubes melt? So, let's see. Now hopefully what you can start to see on the right, which is the one sitting on the metal, we can start to see the liquid, the ice cube is melting, because if I start to move it, it's sliding around. What's the one on the left doing? Nowhere near as much. So this ice cube, placed on a metal surface, is melting much more quickly than if placed on a plastic. Now let's see that again, but with the infrared camera. Okay, so let's think about what it is that we saw and what it can tell us about a phenomena that we have whenever you hold a metal and a wooden object, okay, together. So we have ice that's sitting on top of our two blocks. One is made of metal, one is made of plastic. The ice melts. Why does the ice melt? Well, it's because energy has got to go into that ice. Some of it will come from the surrounding atmosphere, but it's in contact with this. So this thing is hot, as is this. They are both at 20 degrees at room temperature. So these things are hot. They're at 20 degrees. Ice sitting at around about 0 degrees. Okay, and so one of the laws of thermodynamics tells us that energy is therefore going to go from the hot object to the cold object. So we're going to get a movement of energy from the metal into the ice cube, and from the plastic into the ice cube. But what we notice is that it happens quicker in this scenario. And that is because metal is a good conductor of thermal energy. Okay, so thermal energy, it's much quicker to make this movement than it is to make this one. Okay, and that's actually why we define sort of various things as being either conductors or insulators. Okay, things that are insulators, this process happens. It happens slower than it does for conductors. Now this is why if you hold a wooden object and you hold a metal object in each hand, you will feel, your brain will probably try and trick you and will tell you that this is somehow colder because it feels colder, whereas this feels kind of just normal. So your brain might say, oh, metals are cold. This is a thing that we use that term, we use the term cold and say it's a cold object, okay? But actually it's not. They're at the same temperature. They've both been sitting in the room. In this scenario, the thing that is warm is my hand. My hand is at 37 degrees. The metal block is at 20 degrees. And so what can happen, or what will happen, is thermal energy will move via conduction from my hand to the metal block, warming the metal block up until it gets to 37 degrees. And because my hand has lost thermal energy, that's my sensation of feeling cold. If I hold an insulator, well, the same process is happening, but much more slowly, to a level where my body is able really to replace any thermal energy that I lose because I'm losing it so slowly to the wooden block. And that's why it feels warm, even though they started at the same temperature. And oddly, This one will get to a higher temperature more quickly by being in touch with my hand than this one. Bit of a weird way in which that works. Okay, so this is a very exciting demonstration about the difference between conductors and insulators. So what is inside here is basically, this is a little cylinder. Part of it is made of wood, half of it. The other half is made of brass. It's a metal, it's also hollow, so you can sort of... where's my camera? Oh, there. See, maybe I would have seen it. And I've wrapped it with paper, and as we all hopefully know, paper burns. Okay? And I've got over there, oh look, it's a... So there's a, fire, Bunsen burner. So what I'm going to do is I'm going to hold the paper over the Bunsen burner in this, and we're going to see something quite astounding happen that might be a little bit counterintuitive. It's quite difficult doing this in this sort of way. So what we're going to do, put this here. Let's go on to this, all that, and let's heat this up. Oh, there we go. Look at that. Okay. So what's happened is, where is the paper actually burning? You can see there's a line down the middle. There's this wonderful line between where the paper is burning and where it is not. So where it was hottest and where it was cooler. Okay, and that line underneath it is the difference between where underneath it is wood and where underneath it is brass. Okay, now why does it burn? Why does it burn more on the wooden side than on the brass side? Well, what we have is a situation where we're putting heat into this system. So we put this heat into this wooden brass sort of like weird sort of system. If I sort of unfix it. Nope, that's not going to come off very nicely. Under here is brass. Brass is a conductor. So the heat goes into the paper, but then it goes rapidly into the brass, and it shoots down the brass conductor, so it spreads out, okay? And that means that this paper stays relatively cool. On this side, we've got wood. Again, heat goes in, thermal energy goes in, paper starts to get hotter, but the wood is not a good conductor. It does not take, so this end of it still feels quite cold, whereas this end still feels warm. It does not take the heat away from the paper into the wood, so the paper gets hotter and hotter and eventually will start to burn. And what you see is this lovely line between where it's wood and where it's brass. Now, if you put in too much energy, eventually you'll overcome what the brass can do itself, and you do end up heating it up. But it's a wonderful little demonstration, because often people kind of think about conductors being about transferring heat to something, and people say, well, if I hold the end of a metal spoon, it ends up feeling warm because... But yes, but you can also think about conductors, about their ability to transfer energy away from something. And this is a wonderful example of the difference between the two. Let's try another similar demonstration involving something incredibly exciting, a paper cup. This is a paper cup. Why do things like paper burn? Well, this will burn in air because it's surrounded, if we heat it up and it's surrounded by air, one of the reasons it will burn is that it's not able to get rid of the energy. So it's, air is a really good insulator. It's a terrible conductor. And so what happens is you end up being unable to get the energy away, which means the temperature will go up until the point eventually where things will catch fire. So just to demonstrate this is something that will happen, let's set this on fire. So what we can do is warm it up. It'll start to glow a little bit. Now, it actually takes a bit of time to sort of catch fire, partly because the flame beneath it is taking up so much of the oxygen. But I think at this sort of point, if I take it away, there we go, catches fire. Ooh, fire. Okay, so that's all very exciting, and we've got this thing. So because of the way it works. Now, something we're just going to do, I'm going to take this away, put it over here, I don't want that anymore. Right. I'm going to take a paper cup, again, this time I'm going to I have put some water in it. So, same sort of cup, but there's just some water in it this time. And we'll see what happens. So let's try and heat it up. Now this time what we have is we've got paper, which is still flammable, but now instead of the surrounding insides being air, which is a really bad sort of like conductor, really good insulator, we've now got water. Now water's not a great, water still isn't the best conductor, but it's a heck of a lot better than air is. And we've been looking at this for a while. By this point, the other one was sort of starting to burn. We were starting to see it going brown. But here we actually have nothing going on at all. You might be hearing the sort of like the hissing because we are obviously heating up water. We can sort of try coming at this from different angles. Let's actually try and see if we can attack this. So I'm attacking this thing with something that's several hundred degrees, and I can't make it burn. And I can't make it burn because there's water on the inside. We can make the top is starting to brown because we've got this. Oh, hello, that's exciting. Made a hole, maybe. But this is the difference. This is how different materials can be better. If they're better at conducting, water is a better conductor, a way of heat than air. Okay, so we will get conduction from the paper into the water. Water is also a fantastic reservoir of thermal energy. It takes a lot of energy to make a cup of tea. So the water, until the water actually evaporates, this thing is just going to sit there, not doing anything. Even if we attack it like this. I mean, this is weird. Oh, you can see it boiling on the inside. Now, the holes are only being formed at the point where we are above the water level. So you can kind of get a sense of how much water we may have evaporated from here. But what we're not getting is any evaporation. We're not getting fire. We're not getting the paper burning as we were quite used to seeing last time. So that is one of the weird things. As long as there's water in this, we can't set fire to it. There we go. Now, not all conductors conduct equally. Okay, so it isn't just as simple as saying metals good, wood bad, air terrible. As a conductor, even different metals are better or worse at conducting thermal energy in the same way that they're better or worse at conducting electricity. So what we've got, and this is a kind of a classic demonstration, it's hitting it some way. This is a demonstration, it's called the spider. And what we've got is we have different materials. So I've got brass, iron, aluminium, steel, and copper. And what we've got is some metal balls. I see one there. They're sort of stuck in with Vaseline. It's not the greatest. Let's see if I can focus in on that. They're stuck in with Vaseline, and what we can do is we can heat the centre, and conduction will mean that that energy will travel through each one, and the wax, because it's got a very low melting point, will melt, and the balls will drop. Now, if you wanted to make this a perfect experiment, you'd need to make sure that you had the same amount of wax on each ball. That's quite hard to do, so we haven't managed to do that. But we can give a nice sense of the different rates at which things might drop. Now, without understanding the deep set properties of these things, it's actually very difficult to be able to just predict which one it is. Otherwise, it just shows little more than a guess. But brass, iron, aluminium, steel, or copper. Which one do you think is the best one? Well, let's find out. Final thing. And let's go. Isn't this an exciting experiment? I can't even twist it much because then you'd be able to... Ooh. It also starts to smell bad because melting wax is not the most exciting smell in the... is not the most pleasant smell. There we go. Copper. So that was copper, brass, and then that one in the middle. I don't know which one that is. We've still got two that are still going. The fact that copper went fairly quickly, this is one of the reasons copper is so useful. It's used in lots of places because it's a wonderful conductor of thermal energy. It's also a wonderful conductor of electricity for pretty much exactly the same reasons. So it's used, copper is used in various heat sinks inside technological things, but it's also used, and so, gosh, that one there is still going. Still going. Got two that still haven't gone. So there's quite a marked difference in the quality of things as conductors, even though they're all metal. Right, yes. 4 have gone. Waiting for one more. You suck, last one. Really? You still going? How depressing. Let's give you help. Even that did not... There we go. So we went with this. So just in order, we had copper, then brass, aluminium, and then it was iron, and then steel. 5 different metals, but 5 different rates at which they conduct. You don't need to remember the orders of good to bad conductors as far as their metals, but it's just a nice demonstration of the fact that they will not all conduct at the same rate.